Our fourth researcher we're going to hear from today is Kevin Brown from Morehead University. And I'll just pose this question. If you had 12 months and a small box made of circuit boards, how would you use it to reveal the secrets of the universe? And Kevin has done just that.
All right. Well, looking away from Earth a little bit, looking at the rest of the galaxy and the universe, I'm going to be talking about the cosmic X-ray background nanosatellite and a little bit on what Morehead does otherwise with X-ray supernova remnants and the sort. MSU has been getting into the X-ray business, it seems like, recently. So here we go. So I imagine you're probably asking right now, how does a small place like Morehead State, way out in the eastern part of Kentucky, get into NASA type of missions? And the answer is you do it at a very small form factor, one that doesn't require you to have multi-millions of dollars. And that's where the nanosatellite comes around from, and the CubeSat. It's a small box, about 10 centimeters cubed. And in this case, we're using it for measuring the background X-ray emissions from the universe. The foreground science, the NASA mission Chandra, which you see there on the right, is what NASA uses for observing supergalactic or galactic remnants, supernova, that sort of thing. And when they take an image, they need to subtract the background from it. Much like you see in this room, if each one of these lights were a supernova, you would want to take away the glow from the light hitting the rest of the room so that you can see the light better. So that's kind of the layman's terms of what's going on here. Okay, so I'm going to put in a whole bunch of pictures here rather than a whole bunch of text. You can see the text on the posters, poster 11 and poster 20. Stop by anytime. What you'll see there on the top left is a CZT detector. The CZT detector is a very new high-efficiency X-ray detector that's produced over at UC Berkeley and out in California. And once you have that detector, you're able to package it up on the next picture over. It's all shielded with a lead graded shielding, so lead, copper, and tin. And what that does is it blocks all those not so nice particles from getting into the detector. And then once you have that, you need to put essentially a lens, so a collimator on the X-ray detector. That's that picture there. What you do with that is you constrain it to only the viewing window that you want to see the X-rays coming from. And then you need all that supporting equipment around for the satellite. So there on the right, solar panels, star pipper, IMU, magnetorquers, sun sensor, batteries and radio, phasing network, CNDH, more batteries. All of that fits in a little tiny box. In this tiny box, actually. So as you can see, the payload, the X-ray detector's at the top there, and then all the other subsystems take up the rest of the satellite, and in completed form there on the right is what it looks like. From here, the satellite gets taken over to Vandenberg and launched on a Atlas V mission here in just August. This whole development process took approximately 1 year from award to finish. It was quite an endeavor with just about 5 active undergraduate students. So what does all this mean with CXPN? Well, you can start doing neat things with supernova remnants, like Dr. Panuti does at Morehead State. He's on poster 20. What you'll see here is an emission from this supernova remnant on the left. And then on the right, what you do is you map the Chandra. The Chandra data there is in the orange. That's the X-ray information from NASA, and that's after the background's already been removed. And then you map radio emission lines on top of that. So behind all of this, there's tons of science, and you can stop by posters 11 and 20 and get more info. Thank you.